So before we do anything in trigonometry, it's pretty important to understand what it means. Um, this is always the first thing explained. I'm sure you went over in grade 10, but it seems to be once you get caught up in actually doing questions, it's easy to forget what it means. And having a solid understanding of like what you're actually doing and thinking about that as you're trying some of the questions where you're going through stuff will actually make you have a much better understanding as we go through. So before we start though, it's like I said here, it's absolutely vital that you can label the sides of a right triangle as opposite, adjacent, and hypotenuse in relation to a specific angle. That's why I made you practice it twice last week. So that means if we have a right triangle, any right triangle, any size, any shape, any orientation, any way it's flipped, whoops, let me redo that last little line here. Anyway, it's flipped, that you're able to label the sides in relation to a given angle. So let's say this is our angle right here. I labeled it angle alpha. And I wanted to decide, okay, I'm going to call this side A, side B, and side C. I'd have to be able to label which one is the opposite, which one's adjacent, and which one's hypotenuse in comparison to, with reference to angle alpha. So I should be able to say, okay, angle alpha is in this corner right here. And remember, the one thing that's always the same, even if we're talking about angle alpha or if we were talking about this other angle up here, is that the side across from the right angle, that side is always the hypotenuse. So B here, B is the hypotenuse. And so if we look at this other triangle right here, we should be able to say right away, okay, well, this side is definitely going to be the hypotenuse because it's the one across from that right angle. It's always the longest side. I've often just thought about it as the slanty one, but it's however you think about it. The hypotenuse, you can always label first. You should always know that. Then if we look at A and C, these sides of this first triangle here that I have as an example, remember we're labeling, right now I ask you to label it in relation to this angle alpha. So I see, okay, which side is opposite alpha and which side is adjacent alpha. So opposite, we have this side, side A over here. And adjacent to this angle alpha, so next to it, touching, but not the hypotenuse, is that side C. Okay, so however, if we change this up, let's say I said, now I don't care about angle alpha. Let's say I said, okay, now I care about angle theta. The other, I just called it theta, but this angle up in the top corner here. And I said, in relation to angle theta, now I want you to label sides A, B, and C as adjacent, opposite, and hypotenuse. So if you do that, remember the hypotenuse should still be the same. The hypotenuse is always that one across from the 90-degree angle, no matter what. But our opposite and adjacent will be switched out. So here, opposite angle theta, now that side C is the opposite because now we're looking at angle theta. So it's all in relation to the angles we're looking at. And then adjacent to angle theta, but not the hypotenuse, so it's right next to, it's touching angle theta, we have A now. So you should be able to label those. Same with this one right here. Let's say we labeled the corners M, N, and P. And I said, okay, what are all the sides? So a way of writing triangle sides is to say the name of the corner to the next corner, if the corners were named, and put a little line over it to show that it means the whole side. So side MN, side NP, and side MP. And I said, okay, in relation to this angle beta, what is each of these sides? Opposite, adjacent, or hypotenuse? So again, you should be able to say, okay, in relation to beta, well, obviously this one you should have gotten right away. I still had it labeled. NP It's across from that 90-degree angle, so it's the hypotenuse. Then we look at the two other sides. So we had this side MN here, so it goes from M to N, so this side here. That side, we look at it and we say, is this across from, opposite angle beta, or is it adjacent, next to, touching angle beta? So MN is adjacent to angle beta. And then the last side, MP, this far side over here, that was across from or opposite angle beta, which means that is the opposite side. So again, it is absolutely vital that you can do that. If you're still not feeling it, go back to the practice questions from last week and redo them, because that's the silliest thing to make a mistake on. Okay, so moving on. So again, the idea of this lesson is that you get like the point of trigonometry and why it's a thing and what we're actually doing. So it helps to look at the word itself. So trigonometry is from Greek words, I don't know how to pronounce it, trigonon, meaning triangle, and metron, meaning measure. So this makes sense because trigonometry describes and then takes advantage of and uses the properties of the measures of triangles. So it all has to do with measures of triangles. That's going to be angle measures, that's going to be side measures. And this is very important here. The invention of trigonometry, which I looked up, it seems that it was invented in ancient Egypt and ancient Babylon, and then spread to India, where they used it to make some of the first astrological or astronomical, not astrological, astronomical calculations between the stars. Actually, probably used it for astrological too. Anyway, so this is important. The invention of trigonometry came from the discovery of consistent ratios that occurred in right triangles with specific angle measurements. So the invention of trig came from the discovery of consistent ratios that occurred in right triangles with specific angle measurements. If that doesn't make sense to you yet, don't worry, I'm going to show you some examples. Before we do that though, just a really quick reminder, what's a ratio? Because if I say consistent ratios, I definitely want you to understand what's a ratio. So reminder, a ratio is the measure of one thing in comparison to the measure of the other. So if I said, for example, I had rice for dinner last night, and the ratio of water to rice, and you sometimes use this colon to show water to rice when you're cooking rice. Is 2. Sometimes it's written as 2 to 1, but the ratio of water to rice when you're cooking rice is 2. So that means when I take whatever I'm adding in, I take the amount of water and the amount of rice. And if I divide them, so if I take the amount of water and the amount of rice, it should equal 2. And that means that should always be consistent. So no matter how much rice I want to make, I should add an appropriate amount of water so that when I take the amount of water and I divide it by the amount of rice, it always equals 2, or else my rice won't work out. So like, let's say if I wanted to make 1 cup of rice, to make this ratio of 2 work out, I'd have to have 2 cups of water. But last night, I did not make 1 cup of rice because that's too much rice for me. I made 3/4 of a cup of rice. And I had to figure out, okay, I need this number on the top to be twice as big as that, so that when I divide it, I get 2. So I added 1.5 cups of water. So a ratio means, remember, it is a representation of one quantity in relation to another quantity. And we do that by dividing, and then describing the number you get when you divide is a ratio. So I can write that down. So ratio is the relation between two quantities, and it's expressed as a number by dividing one quantity by the other, which you just saw here. So it's the relation between two quantities. In this case, it was the quantity of water and the quantity of rice. And it's expressed as a number, which I said the ratio of water to rice when cooking was 2. So that number that we got by dividing one of the quantities, so the amount of water, by the other quantity, the amount of rice. So if we had 2 cups water divided by 1 cup rice, okay, that's a ratio of 2. And so now we're going to look at ratios of triangles. So on your paper, I'd like you to draw 2 right triangles, and I'm going to show you which ones I'd like you to draw. We're going to draw one that's a little smaller. Looks like this, right angle here. And then I want you to draw one that's bigger, but it looks exactly like that one blown up. So it should be the same proportions. So it just looks like a bigger version of the same one. And we're going to label these. So I'd like you to label in the bottom corner of each of these. We're just going to look at the bottom angle for now, just for fun. I'd like you to label theta in the bottom corner of each of those. Okay, and then we're going to write in the following measurements for all of the angles and sides. So you're just going to copy those down. Okay, so for our small triangle, the bottom side is 7.2 centimeters, and the up and down side is 4.5 centimeters, and the hypotenuse is 8.49 centimeters. The bigger triangle, the bottom side is 18 centimeters even, the up and down side is 11.2 centimeters, and the hypotenuse is 21.2 centimeters. And importantly, I wrote, the reason I used theta here is because I wanted to show that this angle and this angle are the same. They're the same angle apart. Even though these are different size triangles, the angle is the same. So both of these I wrote up here are 32 degrees. So if you want, you could keep theta in the corner, or you could replace it and just write 32 degrees in each corner. It is up to you. So we're imagining right now that these are 2 differently sized, well, I mean, they are 2 differently sized triangles, but they have the exact same angle in this corner. And if we think about it, remember that all of the angles in a triangle are supplementary, so they add up to 180. This one's 90, and this one's 32 in both of them. So these other angles up here are also going to be equal. They're going to be 180 minus 32 minus 90, which gives us 58 degrees, I think. And so they would both be 58 degrees. So these triangles, this means they're the exact same shape, just one is a lot bigger than the other. So they're the exact same shape, exact same proportions, means that one isn't like short and squished and long. That would be a completely different shape, and they would have different angles in these corners. So these are different sizes, but the same shape, meaning they have the same angles. So again, what I said was up here, the invention of trigonometry came from the discovery of consistent ratios that occurred in right triangles with specific angle measurements. So now we have 2 right triangles here that each have the same specific angle measurement of 32 degrees. And we're going to look at some of the ratios. Before we do that, though, remember I said it's going to be very important that we can accurately label hypotenuse, opposite, and adjacent sides. So in relation to theta, that 32-degree angle on both triangles, please label the opposite, adjacent, and hypotenuse. So remember, the hypotenuse is always the one across from the 90-degree angle, across from the right angle. And the opposite is the one opposite the angle we're looking at. So we're looking at this 32-degree angle. So the opposite for the little triangle would be that 4.5, and for the big triangle, it's the 11.2. And then the adjacent side is this bottom side for both of these. Okay, so what I'd like you to do is I'd like you to calculate, okay, for this triangle, the small triangle, here, this small triangle, I want to know what's the ratio between the opposite and the hypotenuse sides. So if I said, okay, what's the ratio between the opposite and the hypotenuse side lengths? So we're trying to figure out, okay, if we just took 4.5 centimeters and we divided it by the length here of the hypotenuse, 8.49 centimeters, we literally just put that in our calculator, 4.5 divided by 8.49, and we end up with 0.53. So our ratio of this opposite side to the hypotenuse is 0.53. So I'd like you guys to calculate, okay, for this big triangle, what's the ratio of the opposite of the big triangle's opposite side to the big triangle's hypotenuse side, and round it to 2 decimal places. So when you do that, you take the opposite side, that 11.2 centimeters, and you divide it by the length of the hypotenuse side, that 21.2 centimeters. And when you do that, 11.2 divided by 21.2, you end up with 0.28301, which, or 0.528, which you round to 0.53. So, interestingly enough, even though these triangles were completely different sizes, because they're the same shape, the ratio from this opposite side to the hypotenuse side is the same. So it means, like, you can see it's about half-ish. It's 0.53. So you could say, okay, in triangles where there's a 32-degree angle in the corner, and right triangles where there's a 32-degree angle, the opposite side is about half of the length of the hypotenuse side, always. And you could have seen that. You're like, okay, 11.2, yeah, it's about half of 21.2. And here you could say, oh yeah, 4.5, it's about half of 8.49. So that is true, though, specifically for these two sides, this pair of sides. So it's true for just this pair of sides, and it's true for this specific 32-degree angle. So that's a really important point, and I'm pretty sure I wrote it later. Did I write it later? Maybe? Yes, I did. Okay, so we'll get to that. So all of these ratios, I just picked opposite to hypotenuse, but you could have compared any two sides. You could have compared opposite and hypotenuse. You could have done the ratio between adjacent and hypotenuse, or the opposite and adjacent ratio. And so to make life easier, because it's a lot of words, they just gave each ratio a specific name. So each, like, side to side ratio, so each combination of sides has a specific name. So for any, like, specific angle, so here it was 32 degrees. So the ratio of its opposite side to its hypotenuse side, that one we just did, is called the sine. They just named that ratio, means it's just called sine. So if you take the length of the opposite side and you divide it by the length of the hypotenuse side, you end up with a number, a ratio, that we call sine. So that ratio is called the sine of that angle. And the way we write that is a little bracket, and we would put the angle in there. I just put in theta for now as like a stand-in, but we would put the angle in there. So if we wanted to describe what we just found up here, we would say, here, let me get rid of this extra calculation. We would say that, okay, so for a 32-degree angle, the ratio of the opposite over hypotenuse was 0.53. But if we had to write that in a sentence, we would literally have to say, for a 32-degree angle, the ratio of opposite to hypotenuse is 0.53. That takes a really long time. So instead of this whole sentence right here, for a 32-degree angle, the ratio of opposite over hypotenuse equals, we can just write this using this specific name. So we can say instead, to shorten this up, we can say the sine of 32 degrees equals 0.53. So what we're saying here is this means sine, remember, means the ratio of the opposite side over the hypotenuse side. So sine, the word sine, that's what it means. So that's what it stands for. And then this 32 degrees in brackets is saying that's only true for a 32-degree angle. And we could check that if we use another triangle. Let's say we make this triangle right here, and we change this to, this is now a 51-degree angle. And I'm going to write up the measures of the sides really quickly. Okay, so for this triangle, we have the bottom side is 7.1 centimeters, the up and down side is 8.77 centimeters, and the hypotenuse is 11.28 centimeters. And we're just going to check, okay, so for this triangle, which is a different shape, right? So if we compare these are completely different shaped triangles. This one right here, they're all right triangles, but these two had the same shape because they had all the same angles. Their sides were at the same angles to each other, whereas this one is a different shape. So for this specific shape, where you have a 51-degree angle in this corner, what is the ratio of its opposite side to its hypotenuse side? So what's the ratio of its opposite side to its hypotenuse side? So if you plug that in your calculator, you can just say, okay, 8.77 divided by 11.28, and you end up with, rounded to 2 decimal places, 0.78. So if we wanted to describe this, we could say a long sentence like this. You could say, in all right triangles with a 51-degree angle, the ratio of the opposite to, just move this out of the way, the adjacent, or sorry, to the opposite to the hypotenuse sides is 0.78. So I could write that, but that, if I made you write that all the time, that would be very irritating. So instead, they said, okay, well, the specific name we came up for, which I looked into it, it's a very long history. It's got like Sanskrit and Latin and Greek origins. So we'll just memorize it. It has to do with like bows and anyway, whatever. So they said, we'll name this ratio. The ratio of opposite over hypotenuse, we'll call it sine. They abbreviate it with SIN. And we can say, we're trying to say in all right angles with a 51-degree angle. So the sine, where the angle we're comparing to is 51 degrees, is 0.78. So this is just a compact way of writing that. So that just says the sine of 51 equals 0.78. That means when you have a triangle with a 51-degree angle in the corner and you label its sides in relation to that angle, and you take its opposite side and you divide it by the length of its hypotenuse side, the ratio is always going to turn out to be 0.78. So that's, this right here is just a compact mathematical statement. The other compact mathematical statements we're going to look at is the ratio of the adjacent side to the hypotenuse side. So if we were going to compare, okay, how does the adjacent side of the hypotenuse side like relate for a specific angle? We call that the cosine, which is abbreviated COS. of that angle. So the cosine of a specific angle is just another way of saying, okay, what's the ratio between the opposite or the adjacent and hypotenuse for a triangle of this shape. And then the other ratio we're looking at is the opposite to the adjacent side. So if we want to compare, okay, how does the opposite side of this triangle compare to the adjacent side of a triangle shape like this? We just call that the tangent of that angle. So we only, in our first example here, we only calculate, well, actually both examples, we only calculated the ratio between the opposite and the hypotenuse sides, but we could have done any. We could have said, okay, what's the ratio between the adjacent and the hypotenuse? We could have said, what's the ratio, and we could have divided the 7.2 by that 8.49. We could have divided that 18 by that 21.2. We could have also compared the opposite and adjacent sides. So it's just different ways of comparing different sets of sides. And remember, very important here is that this is for a specific sized angle, and it's for every triangle with that specific sized angle, the ratio of the two, like, say, comparable sides will be the same. So every side-to-side ratio has a specific name, and it's very important that it's for a specific angle measure. So it's only true in triangles of the same shape. I mean, that makes sense. Like if you had if I had a pen, this pen right here, and I made it twice as big, we'd expect it to get twice as long and twice as tall. That makes sense. If you have a differently sized pen, then it's not going to be the same ratio of sides. So it's only for a specific shape of triangle, and the easiest way to describe shapes of triangles is to describe the angle between their sides. So these are the three trigonometric functions we're going to use. There are others. They just compare in different ways. So for example, there's one called cotangent. So if you have the cotangent of a specific angle, that's the ratio between its adjacent and its opposite sides. So, but you'll notice we already have one comparing, we have tangents already that compares opposite to adjacent. So because we have all the combinations possible with sine, cosine, and tangent, those are the ones we're going to use. The other ones you can use, but they just give you more options of like different ways of combining these. So like that would be like if I had said, instead of doing the water to rice ratio, if I had done rice to water. But both of them we can use to figure it out. So to make our lives simpler, we just stick with 3 and be happy with that. So, but it is important to remember, okay, which word here between sine, cosine, and tangent corresponds with which ratio, and to not mix up this order, because like I said, that's a completely different ratio. So to remember that, we have a mnemonic, which I'm sure you've heard. It goes so, toa. And the point of this mnemonic is just to remind you which word goes with which ratio. So shows us, so we always start with our trigonometric ratio word. So sine, that's the S is for sine, of a specific angle equals the opposite over the hypotenuse. So that's the sine of a specific angle is the name for the ratio when you take its opposite side and you divide it by its hypotenuse side. The ka is same thing, except this time it's cosine of a specific angle, is the name for the ratio when we take, oh, I'll put in capitals, when we take the adjacent side and we divide it by the hypotenuse side. And toa is just to remind us that the word tangent of a specific angle represents the ratio between that angles opposite and adjacent sides. So SOHCAHTOA just helps us remember, and I still use SOHCAHTOA when I'm writing things down. So it's a helpful mnemonic, but it's just there to help you remember like which ratios are described by which words and what order the ratio goes in. So now the question is, okay, how did we figure out all these ratios? And the answer is, back in the day, ancient people made a ton of triangles, like out of wood, out of cord, out of whatever, and they measured the sides and the angles, and they calculated ratios over and over and over and over again to check, yes, are these all the same? And then they just did it for every single possible angle. So just like we did up here with these triangles, where we just figured out, okay, the ratio of the opposite side to the hypotenuse side when we have a 32-degree angle, so the sine of 32 degrees, no matter what our side lengths are, when we divide them and we find that ratio is always going to equal 0.53. But then remember, we did it with a differently sized triangle, a differently shaped triangle, and we found that when the angle we're looking at is 51 degrees, then the ratio of its opposite side to its hypotenuse side is completely different. It's 0.78. So what people did is they went through and they're like, okay, what if it was a 1-degree angle? What if it was a 2-degree angle? What if it was a 3-degree? And all the way through for all of the options. And then they just put this together into these giant trigonometric tables. So back in the day, if you wanted to know what the ratio is between two sides for a specific angle, you had to actually look it up. So when my mom was in school, the calculators of the time didn't have these ratios stored in them. So if she wanted to do anything with trigonometry, she had to actually look it up. So she had, let's find our 32-degree angle here. So she was looking at a 32-degree angle and she wanted to know, okay, what's the ratio between the opposite side of a 32-degree angle and the hypotenuse side of a 32-degree angle? She would have said, okay, opposite over hypotenuse, that's sine. So she would have found, okay, this is sine, this whole column, and she would have gone down to 32 degrees and found, oh, it's 0.5299, which we rounded it to 0.53. But you can see that it's accurate. That's what we calculated, 0.53. So originally, people just measured a whole ton of triangles just to make sure they were exact and correct. And they put this together into a large table. And it gets even worse because when you want to make really exact calculations, like in space, they use trigonometry to measure the distance between different stars, but like they have to measure a very tiny angle. So if you're looking at a star and then you measure the angle from that star to another star, it's going to be something tiny. Sometimes it could be like 0.00289 degrees. And you'll notice that's not an option on here. So you have to go to an even more specific trigonometric table and an even more specific one, and it got really complicated. So the good news is you no longer have to look up all the specific ratios because you have a fancy-dancy scientific calculator, and all of those ratios are already stored inside this little machine. So all you have to do is ask your calculator to tell you the ratio. So when you ask your calculator to like do the sign of a specific number, it's giving you the ratio. So if you ask it to do the sine, remember sine, SOHCAHTOA. So sine represents that ratio between the opposite and the hypotenuse sides. So when you ask it to do the sine of a specific number, it's actually just giving you that ratio of the opposite side to the hypotenuse side for all sides of triangles with whatever specific angle you told it. So that number you give it is the angle size. So we can check that in your calculator. If you type in sine of, remember we did 32 degrees earlier, sine of 32 degrees. So in your calculator, sine 32 should should look just like this, sine of 32 degrees, and you hit enter, you get, on my calculator, it says 0.529919264, which if we round it to 2 decimal places is 0.53, which is the exact ratio we calculated earlier. So that's saying that's just, our calculator just has the information stored. And that's going to be really helpful because it means that we can actually use this information about ratios to help us find things we don't know, as long as we know a couple things to compare them to. So as long as we know a couple things to compare them to, we can figure out some stuff we don't know because these ratios are always consistent. So in your calculator, the only thing that might throw you off is there's 2 different ways that we use to measure angles in math. One we use mostly for triangles, and we use it a lot for like maps of land, and that's degrees. That's what you've seen before, like 1 degree, 2 degrees, 90 degrees, 45 degrees, 360 degrees. The other way of measuring angles, so other way of measuring angles is called radians, and that's relating the angle size to the properties of a circle. So if you do higher level math later, you will work with radians, but for now we just need to know that they are different. So if you have like a 45-degree angle, that's one way of measuring it. If we measured it in radians, we'd use a completely different measurement. It's like measuring a distance in kilometers versus in miles, just like completely different. And if you were going to put in, like if you got pulled over and the police officer said, how fast were you going? And you said, well, I was going 100 kilometers per hour. And they're like, and they said, no, you weren't. You were going 100 miles per hour. And you're like, psh, same diff. I don't think they would agree with you. So they're completely different units. So we just have to make sure that our calculator is giving us, like is ready to go for degrees. So you'll see in your calculator, if you look at the very top, you should have a little icon somewhere that either says D or R. D is for degrees, R is for radians. You do not want it in radian mode. You want your calculator ready to go in degrees mode. Just like when you're in Canada, you want to be looking at the kilometers per hour in your car and not the miles per hour. So if you're unsure how to do that, I can give you a little bit of a tour of my calculator. Yours might be slightly different. So if you can't figure it out, you'll see at the top of your calculator, it has a brand name and a model number, or a model like name. So mine is like Casio FX something, something, something plus. And if you Google that and how to switch from degrees to radians, a page will pop up. Your calculator has a huge long manual that you probably threw out when you got it, but they're all online. So I'll show you on mine, but if you can't figure yours out, you can Google it. If you still can't figure it out, just send me a picture of your calculator and I'll tell you how to find it for your calculator, exactly how to switch that over. And if earlier when you did this and you put in sine of 32, if you did not get that number, that means that your calculator is currently in radians. So if you did not get the same answer, then your calculator is currently in radians and you need to switch it to degrees. If you did get this same answer, then it's good to go. That's like you were going 100 kilometers per hour in a 100 kilometer per hour zone. So you're good to go. Okay, so here you can see a graphic of what my calculator looks like. And you can see this on the right-hand side here is like just a giant pop-up of the screen. So you can see up here, mine has the little letter D, which means that it's currently in degrees. But if it had here a letter R, or some calculators just show nothing when it's in radians and they show a D when it's in degrees, or the other way around. I know it's confusing. I wish we all had the same calculator, but we don't. So if you needed to change it, you are going to have to go into the settings, and I'll show you how to do that on mine. Again, yours might be slightly different. You can use Google, but it's probably going to be something somewhat similar. Okay, so on mine, if you click, you have to go into the setup menu, and you can see that in mine, setup is in yellow, which means that I'm going to have to hit the shift button to get into the setup menu. Just like on your keyboard, the exclamation mark is over the 1, and so you have to hit shift to get to the exclamation mark. And then on my screen, this pops up, and it tells me, this gives me the opportunity to change some of the settings. So if I wanted it to go into degrees, I would hit 3. If I wanted it to go into radians, I'd hit 4. So I mean, I could switch mine to radians. And now you see on my screen, there's a little R. Now, if I did that same thing as before, that sine of 32 degrees, which we already said should always be 0.53, I do not get that. I get a different answer. And that's because my calculator was in radians. That's like just reading 100 off of your speedometer and traveling that speed when you're going 100 miles per hour, and you should be going 100 kilometers per hour. So if that's the case and your calculator is accidentally in radians, you would just need to change it by going into that menu and then picking the option for degrees. So mine is 3 here. And then now when I do that, you see it turns out to the right number here. So it's very important that your calculator is in degrees. Like I said earlier, the majority of mistakes, silly mistakes in trigonometry, come from mislabeling your sides. Second most common mistake is that your calculator is actually accidentally in radians when you want it in degrees. So just make sure that you know how to switch it back and forth. And again, if you're confused, Google your exact calculator name. And if you still can't figure it out, send me a picture of your calculator, because then I can tell you based on your calculator what the directions are to change it. Okay.